at UBC since 2002, and you are an associate, or are you full professor now?
Full.
Full professor. You need to update your bio online.
Right, yeah. Sorry about that.
That's what I thought.
Let's get right on that.
She received her PhD from Stanford in 2000, and prior to that, she was on the technical staff of the Geometry Center and did mathematical visualization work there. And she's one of the leaders in the information visualization community. I had the pleasure of working with Tamara back in 2004, 5, and 6 on what became the NIH NSF Visualization Research Challenges Report, and got to know her very well from back then. I have been trying to get Tamara to come and give a distinguished lecture for a little while now, and so I am very pleased that she has come, because I think she is doing some fantastic research, and you will enjoy seeing some of that today. So please join me in welcoming Tamara Munzner.
Thanks, Chris. I am delighted to make it here. So today, what I'm going to focus on is dimensionality reduction, and a bit of a pun intended, from several angles. So what do I mean by that? So let me start out by saying, well, what do I mean by dimensionality reduction? It's a slightly overloaded word. People use it in a lot of different ways. So very, very broadly speaking, I'm talking about any way that we're mapping data from some dimensional space in which we've measured it into some lower dimensional target space. And so when would people do this? Well, it's when you can't directly measure the thing you actually want. And so you don't use this with all high-dimensional data, but if you have some reason to conjecture that the dimensionality of your data set is smaller than the dimensionality of measurements, then that would be a reason to use it. Let me just check my volume. I'm kind of hearing myself cut in and out. So how about that? Let's see if I cut in and out. If I cut out, someone should wave their hand, and that will make it obvious. When I do this with my head, no? Yeah? Okay. All right. Hopefully this is now registered with respect to my larynx. All right. So some of the reasons why people use it, so you conjecture that there's some true dimensionality that's smaller than what you were able to measure, and that is somehow something that was latent in your data. So sometimes these are called latent factors or hidden variables, and you're trying to recover them from some verbose way of measuring your data. So just a quick example, let's say you've got some kind of measurements on a brain tumor, and this might be a 9-dimensional space you can measure, but of course what you really care about is, well, is it malignant or benign? And let's say here's an example where we've reduced in dimensionality to 2 dimensions, we've color-coded according to some conjectured classification of malignant versus benign, and then, well, what are we doing here? In terms of visual data analysis, we're looking at that and checking, do I actually believe this classification based on the spatial position of the points? Versus this conjectured classification that I've color-coded. So that would be a typical use of VR in a viz context. So why do people do VR? Well, there are 2 major reasons, and one is to improve the performance of some algorithm that you intend to run downstream. Typically that's to avoid the cursive dimensionality. And then another somewhat different use, and the one I'll be focusing on in this talk, is directly to do some kind of data analysis. And in particular, if you're going to look at the output, then let's think about that as visual data analysis. And that's going to be my focus for most of this talk. To check again, am I cutting in and out, or am I actually doing the right thing with volume? Mostly. Okay. I wonder whether I should play with this more or keep going. All right, I keep going. So, back to my title with angles of attack. What am I talking about? Well, I'm going to talk about ways attacking this problem that include designing better algorithms, designing systems, designing tools specifically to solve the problems of some real world end user, ways of validating or evaluating whether or not any of these worked, and also creating taxonomies to try to characterize some existing work. So my argument, which I'm going to try to hopefully prove to you over the course of this talk, is that there are benefits from attacking in these multiple directions, that it gives you a parallax interesting, and that you can have the outcomes from these different cross-pollinate with each other. So I'll tell you a progression of questions that I personally had I've been working in DR on and off for around a decade or so. And I started out with this question of, can we design dimensionality reduction algorithms or techniques that are better than the previous ones? This was a very obvious starting point. And then something a little trickier. Can we build a DR system that real people use? And then another one, when do they even need to use this? When do they need to look at the output of dimensionally reduced data? And then that leads to another even bigger question of, how do you figure out what people need anyway? And then finally, how should they look at DR output? So how can you tell if you're drawing the right picture? How can you tell if some automated metric you have actually matches up with human perception? So it turns out, to sum this up, the questions really became about why and how do people use dimensionality reduction in a visual data analysis context. So then this led to even more questions. I found a lot of open questions, which are, how are real people actually using the tools and techniques that researchers have proposed for DR? In particular, does real usage match up with what we think, or we hope, or we assert, or we assume? And why are they using it? That is, what are their goals and tasks at some abstract level that's a bit more generic than a specific domain problem? And then finally, coming back to, is it working? So how do their goals actually match up with what we assume, or our algorithms assume, in terms of both algorithms and benchmarks? And also, does our current suite of tools actually then meet their needs, or are there open problems that would really benefit from future work? So this led to a project that lasted a couple of years, DR in the wild. And this is joint work with Michael Sedelmeier, Matt Bramer, and Stephen Ingram. It's still a work in progress. What we started on a few years ago was 2 years of talking to people in a number of different domains. And this is a qualitative study to try to figure out, what are real people doing? In the wild is a buzzword out of HCI, which means talking to people in the field as opposed to doing some kind of experiments in a controlled setting in a lab. Use that buzzword. And what we did is we talked to a couple dozen people that are regularly doing high-dimensional data analysis over a number of different domains, ranging from journalism to computer vision to computational biology. And so it's a work in progress. Stay tuned. Hopefully you'll hear some final results one of these days. But what we came up with was a taxonomy of abstract tasks for people doing dimensionality reduction. So to try to generalize across domains and figure out, what are the unmet needs of the users? So this question of why and how do people use DR was why we started this project. And it turns out that since this was a longitudinal kind of over time study, this has been interwoven in a fair amount of our recent work. So these are going to be the questions that are weaving through this talk. And early results from this study, even though it's not yet formally published, have informed a bunch of our recent work in the area, because we started thinking about this a while ago. So the specific questions and answers that I'm going to focus on in this talk are, how can we design DR algorithms that are better? Can we build a system that real people use? When do people need to look at the output of DR? How should they look at it? And then more generally, why and how? So this question is, how could you even begin to answer these questions? These are pretty broad. These span a lot of different levels. There are a lot of different ways to try to validate whether the work you've done is any good. So I'll be alluding to in this talk this idea of levels of design. So I realize many people in this room might have already drunk the Kool-Aid, but I'm curious, has anyone here not heard of the nested model, or is anyone already deeply familiar with it? So heard of it? Enough not that I will actually go into these slides then. So this was a model I proposed a couple of years ago about a way of thinking about validation methods as they relate to different levels of design. And the idea here is to try to separate out some concerns into 4 different levels. And the reason these are interesting is that you have different ways of trying to evaluate whether it worked at these different levels. So to borrow language out of software engineering and computer security, that there's different threats to validity at these levels. So one is to think about characterizing the problems of a domain user, which is, if you get this wrong, that means you misunderstood the needs of the user. So all of your downstream choices, no matter how perfect they are, won't do any good if you're not actually solving the problems that need solving. Then the next level down is an abstraction, where as a visualization person, you decide what are the abstract data and tasks that people are doing that might be from very different domains that map to the same abstraction at the visualization level. And if you get this wrong, then the threat is that you could be showing them the wrong thing. Now, one level beneath that of design now is the actual techniques for visual encoding and interaction. And if you get that wrong, then the way you show it doesn't work. And then finally, at the algorithm level, yet another level of design. And what's the threat? Well, something like your code is too slow. So what's interesting about this is to try to split up your goals according to these 4 levels so that then you can match your validation technique with your design level. Now, I'm not going to go into detail about this slide. If folks are curious, there is the paper available from a few years ago. But the key thing is to try to divide validation methods ranging from, at the algorithm level, things like measuring system time and memory or doing computational complexity. Those are very different techniques than what you might do at the visual encoding level, say of running a lab study. And those are different in turn than trying to decide, do I have the abstraction right? You can't check that with a lab study where you're telling the users to do a particular thing. So in that case, a better method might be a field study. So there's a lot of these different levels of design, and you can adapt your validation method to them. So what I'm going to be talking about here is, even though no single paper would typically employ all of those methods in the previous slide, then your paper would be about 2,000 pages long and take you about 17 years to write. So we don't typically, in any single project, try to attack all of these levels at once. Usually you try to pick the method based on what are your contributions, what is your angle of attack. So one thing I'll be doing in this talk is I've picked a deliberately broad set of methods for validation for a bunch of different projects that I'll talk about to try to help give some clarity on what kinds of questions are particular methods best suited for answering. So the outline is, can we design better algorithms? Can we build a DR system for real people? How do we show the results? And when do we need them? So what I'm going to focus on at the beginning is this question of designing better DR algorithms. This is both the place we started quite a while ago and also the place we continue coming back to. So we'll talk also about more recent work. Both of these are algorithms for MDS. One's focusing on the GPU, one's focusing on costly distance metrics. So some earlier work, this was joint with Stephen Ingram and Mark Alano, about trying to do a new multi-level algorithm for MDS that ran on the GPU. So first of all, when I say MDS, multidimensional scaling, somewhat confusingly, this term is used for an extraordinarily broad set of techniques, including both linear and nonlinear methods. And so among the families in MDS are the so-called classical scaling, where you're thinking of this as an optimization problem where you're minimizing a method called strain. And this includes a lot of the systems that come out of the machine learning literature, these spectral methods, often the so-called Nystrom methods. And there's now some really nice algorithms for doing this in O of n time. And some of the limitations that we came across are that for particular kinds of very high data that's sparse, for example, document collections, there's actually some serious quality problems. Now, there's another whole family of methods, the so-called distance scaling methods, where, considering it as an optimization problem, you're minimizing the metric of stress rather than strain. So you're minimizing on something different. There's also been a series of threads of work on some of them come out of the optimization literature. There's a nice n-squared algorithm, Smakov, which gives you high quality but has some serious speed problems. There's been a lot of work, particularly in the Infobit community, on force-directed placement. These were also roughly n-squared, but they also ran into some quality problems of getting stuck in local. So what we wanted to do was try to combine the best of both worlds, where we could have an algorithm that was linear in the number of points and was both high quality and high speed. So I'm not going to go into huge amounts of detail about it in this talk. I'm just giving you a little taste. But after thinking a lot about the various methods, we decided that the stochastic force algorithm was a very nicely suited approach for getting a high-speed GPU algorithm. But one thing that was interesting was once we had an algorithm that was fast enough to do systematic testing, we found that there was a certain amount of cherry picking that had been at work in previous approaches where they would show nice samples. But then when we actually systematically were testing it, we'd find that sometimes we'd get these nice results, and then occasionally things would go drastically wrong. And the bigger the data set got, the more often things would go drastically wrong. And here's a really simple data set to show that if you just start with something very simple like a grid, then often you'd end up with a twisted grid. You wouldn't even recover this very simple structure. And so one of the things we tried to do was design an algorithm that used this idea of stochastic force as a module inside a multi-level system that was custom designed to work well with GPU parallelization so that we could actually get the much better convergence properties, even though we were still using something that was stochastic force at the core. And here's an example of the kinds of data sets we found that do so well with the spectral methods that actually responded nicely to this kind of stochastic force randomization approach. And so here's an example of that we actually were able to see some cluster structure using Glimmer that just was completely hidden using one of these spectral methods. In this case, it was pivot MDS. But this also actually brings up an interesting point. So this is a data set with roughly around 30,000 points and also 30,000 dimensions, as is typical in these high-dimensional document data sets. And the question often comes down to, well, if you see a number for stress, what does that mean? Is it any good? Can you actually see structure in the data? And so one of the things we needed to do was a mix of actually looking at these metrics and then qualitatively looking at the results and trying to decide where is good enough. And the question of what is good enough actually gives, it's a different answer for different kinds of data sets. Typically, you don't know a priori what kind of residual error you're going to get. And so being able to draw in on this graph roughly which of the methods did show you visible clusters versus which did not was something where we needed a mix of looking at things qualitatively and also running the numbers quantitatively, and then seeing that indeed this Glimmer method was basically speed competitive with the spectral methods, but actually gave higher quality results. Now, just to go back and think, I'm going to systematically go through and talk about methods and outcomes with the different projects that I'm talking about here. What did we do here? Well, very standard quantitative benchmarks for algorithms, speed and quality. But one of the things that was interesting compared to some of the previous work that had appeared, particularly with stochastic force algorithms, to try to systematically compare and understand what were some convergence problems with the previous work that hadn't really been noticed before because people have been spot checking with a couple of key benchmarks instead of systematically trying to look at a number of different data sets of different sizes. And we also did need the mix of quantitative algorithmics of metrics and these qualitative judgments of layout quality to try to understand when does it matter. If the metrics give you different answers, when is it just minor variations versus structure that you systematically can or can't see? So in terms of the outcomes of this project, what we tried to do is understand what were the characteristics of the data sets where we were doing much better than the previous work, and ended up realizing that in this case, it was about the data being very sparse. Now, one good question is, so then what? So you've made an algorithm, and you release it out into the world, and what happens? What we saw is some interesting results in terms of what were some of the places that it did well versus ran into limitations when real users use it. So we find some interesting examples of places where there are characteristics of the data that we hadn't thought about, that other algorithm designers hadn't thought about, that were actually limitations with usage in this. So a number of people were happy with Glimmer and got good results. But there were some interesting examples of results where we could actually do much better. So some much more recent work, this just came out a month ago, was Glint, which was trying to say, what about doing MDS when the distance functions are actually very expensive? And this, again, is joint work with Stephen Ingram. So now I've just told you that there are work with MDS, and we talked about quite a lot of these linear methods. So, starting out with classic MDS back in the 50s, there were some n-cubed methods. Over time, there was a mix of going from n-cubed down to n-squared. Then there's a number of these kind of linear style algorithms, whether it's the spectral methods or Glimmer, the work I just presented, or some work by Joya et al. And others. So if we have these order n algorithms, are we done? Is there anything left to do? Yes?
Just to be clear, you mean MDS in a multidimensional scale?
Yes.
Right. And then the distance matrix. You define what stress and strain are? It's really MDS, but I'm a little not sure of stress and strain.
I wasn't going to go into too much detail about it in this talk, but the short answer is they are different metrics that are certainly not absolutely equivalent, but I wonder whether I want to... I'm not going to take the time to actually flash up the equations right now, but the short answer is different metrics. So if you think about them broadly as you're just optimizing to a slightly different metric, and what's interesting is what are the implications of that, and what kinds of structure are you going to see when you optimize for one versus the other. But yes, I do mean MDS is multidimensional scaling. But I'm actually just about to get to this question of, do you have a distance matrix or do you have coordinates? So you have foreseen my next slide. So in particular, if you're looking at MDS where you've got coordinate data, in this case, you have high dimensional points, some way to calculate distances between them. So here's a very standard benchmark. We've got over 40,000 points, a 9-dimensional data set, and then the older methods are going to take hours. The newer methods are all going to finish in about a second. And in this case, it's assuming a very, very cheap distance metric. So let's think something like straight Euclidean, and then distances are fast to calculate. Now, there's some interesting data sets out there where the distance metric is actually much more expensive. So let's take the case of photos out of Flickr. And a metric like the Earth mover's distance, where what you're actually doing is a much more involved calculation, where you're trying to think about moving colors around between the images. And in this case, if you run all of these standard algorithms off the shelf, they're also going to still be hours. And what's going on here is that the time to calculate distances are much, much more expensive. Ross? We're going to get to that. So the short answer is a lot of them are set up to assume that you do need the full distance matrix, and actually Glint is trying to get at this question of automatically figuring out how little can you do. So before I do that, let me actually just mention for people that are not the two in front who might be wondering, wait, what exactly am I talking about here? When we talk about MDS, there's actually, I talked about two main flavors. Are you minimizing stress or minimizing strain? Another cross-cutting way to think about MDS is, what are you given? Are you given points in a space upon which you can directly calculate a distance? Or are you given some kind of matrix of pre-computed distances? And so really what you have is pairwise distances between any two items. Do you know what the distance is? Now, some algorithms actually can handle either one of these cases. Others assume coordinates. So some algorithms simply assume coordinates as a fundamental way that they attack the problem of speeding things up. So LAMP is one, for example, that doesn't work well with distance matrices. Other algorithms are agnostic, happy to take either one. Either you have coordinates or you have a distance matrix. And then in both cases, what you do is at the end of the day, you end up with a low-dimensional geometry where you do have coordinates in a lower-dimensional space. So coming back to the question that got asked, so wait, do they need the full distance matrix, or do they just handle part of it? So a lot of these methods assume that you have pre-calculated the entire distance matrix. And what they do is they assume that that was a pre-processing operation. Well, okay, maybe it's n squared, maybe it's really expensive. And then once it's pre-processed, here you are, and at runtime, you're simply grabbing points from that matrix.
But if you grab them all, it's an n squared algorithm. Is that the way you're defining it?
That's the way I'm defining it now. Yes. So, and the question is, could we do better? Could we, that once you say, oh, maybe instead of saying, let's pre-compute everything, assume that's expensive, but then at runtime we don't have to pre-compute, is there a way we could actually minimize the total cost of this and not just abstract away that messy little quadratic pre-processing step? So what we're trying to say is, what if you didn't start out with the pre-computed distance matrix and you were actually deciding on the fly distances to compute? Could we do something smarter? And so this question of, do you have very costly distances so that you would even care? If it turns out that all of the distances are cheap, then maybe it's not so interesting to worry about it. What we actually discovered, and this gets back to that Deer on the Wild project, is there's a bunch of interesting cases where you do actually have expensive distances. So here's the kind of standard cheap one where you're using some kind of Euclidean distance. But there's some interesting other ones. For example, what if a distance query actually comes down to doing a database query? Well, then that's going to have some overhead. What if it's one of these more complex calculations like Earth mover distance between some images? What if it's still Euclidean, but you've got 4 million distances? For example, there's an interesting paper by Matusik and Hans-Peter Pfister on looking at BRDF data, right? In their case, they actually had 4 million distances. What if you've got this rather dismal case where there is a human and you are asking them a question? In order to find out the distance between 2 points, you're asking for human judgment. You know, let's count this as bare minimum 10 seconds when you've got these humans in the loop. This turns out to be used a lot in things like psychophysics, marketing, where you're actually asking humans things. So it turns out there's a lot of these interesting cases where people have just been looking at tiny data sets because pre-computing these distance matrices was extraordinarily expensive. So the question was, could we do something where we tried to automatically figure out how many distances do we need, calculate as few of them as possible, and still roughly maintain the quality of these other approaches? And so what we're proposing in Glint is in some ways a simple idea, and all the devils are in the details, which is start out with a very, very sparse matrix, and then lay out the points according to this much sparser distance matrix, figuring out if we've actually converged, and doing this in a loop where we're gradually densifying the matrix. So what we're basically doing is try to minimize the number of distance calculations and possibly do a little more work than we had to by repeatedly laying things out, because what we're assuming is that actually the distances are much more expensive than layout computations, which is kind of the inverse of the traditional problem. I mentioned a lot of the devils in the details. In the paper, we go into more about what's interesting about this framework, and it turns out to be adapting a lot of different kinds of algorithms to work within this framework. We actually instantiated 3 different flavors of algorithms: the optimization smack-up approach, the spectral pivot MDS approach, our own previous work for the force-directed, to see what it's like to have these different flavors of algorithms in this framework. So once again, I'm going to kind of blast through and not go into a lot of detail. I'm covering a lot of territory in this talk, but to pick 1 of those 3, what we did indeed see was that when the distances are cheap, then of course this method of doing more layout work than we have to is more expensive. But when the distances are costly, then it really is a win to have this kind of framework where we're minimizing the distances to compute, where we don't assume that they were all pre-computed. And the quality was roughly equivalent, which was what we were worried about. So we succeeded in that case. Now, coming back to this question of methods and outcomes, this was very much a method of let's run a bunch of algorithm benchmarks. We have a fairly well-characterized problem, and the really interesting things to do now is check for time and quality. So in terms of outcomes, what was interesting about this, going back to that nested model, was the difference between this case and the previous cases were about the data abstraction. That is, it turned out there was this interesting case where the data actually had these very high dimensional distances. And this came about because we ran into people that had this problem. And in this case, what we tried to characterize as being different was, in this case, it was the distance metric, as opposed to in the previous one, it was more about the data set characteristics themselves, about being sparse. And so coming back systematically to, okay, well, then what? Well, it turns out that what we are continuing to do is talk to people who are trying to use this and understand. There's all the cases that make us happy, where everyone's problems are solved. And then what are the limitations from some other, typically it's either the task is different or the data is different in some interesting way, to discover more of these unmet needs. So we are continuing to do this sort of technique-driven work, and hopefully you'll see more work coming out of our group fairly soon, possibly even in about 6 weeks. So the next question I want to focus on is, well, how do you actually get people to use all these tools properly? And what we ended up doing is also doing some work that's not just about let's design a better algorithm, but let's think about designing an entire system so that some of the existing algorithms are used in a way that's more effective. And in particular, can we build a DR system that real people can use? And can we give some guidance? And that was the DimStiller system. And in a moment, I'll say what I mean by real people. So this was also joint work with Stephen Ingram, some others, including Veronica Irvine, Melanie Torrey, Stephen Berg, and Torsten Moeller. Now, this question of who might use dimensionality reduction, we discovered from talking to lots of people that there are 2 interesting axes that you think about. And one is, well, how much math do you know? So that's our vertical axis. So let's think of near the bottom, they don't know what a mean is. Okay, there's not so many of those people in this room. But let's think about this middle place. Well, yeah, I took a stats course when I was an undergrad. Maybe that was many years ago. And then at the top of this axis, of course, you know, I had a best paper at NIPS last year. I know my DR algorithms down cold. So if that's one axis, then what's the other? how much do you know about your data? So, you know, over here is, well, 10 minutes ago I got some email, here's this file. I guess, well, maybe there's 20,000 points. I don't really know a whole lot else. What the heck are these columns? And then, you know, over here at the end of this axis is I've just studied this data intensively for the past 5 years. I know everything there is to know about it. This is data that is fully understood. Okay, so according to the axes, then let's think, when do we care about using a DR system? Now, at some level, when you're way down here, the answer is you probably don't want to use a DR system at all. You've got some learning to do before you get there. And so we're really not focused on pedagogy of the very basics of dimensionality reduction. And now, this spot, if you really know everything there is to know about your data, well, you probably don't need to do any more analysis. But there's 2 more areas. What a lot of the previous work has been focused on is people that are relatively sophisticated in terms of their knowledge of the mathematics of DR in particular, and what you're trying to do is fairly well defined, and then the more you know about your data, maybe the less you need to know about the algorithms and their assumptions. Okay, so what about that big hole in the middle? So these are the people we're calling middle ground users. They might know a lot about math for the particular domain science that they're doing, but maybe not so much about the mathematics of dimensionality reduction in particular. And our conjecture was that there are a lot of these kinds of people out there. They're actually using DR now, perhaps not always effectively. And could we build a toolkit that actually helped them do DR in a more systematic way? So when I say this idea of, well, how do we guide the users, what do I even mean by guide? And in this case, there's 2 flavors we want to talk about. If you think about that you start out with some data set that's very verbosely described, and at the end you want to get to this nice, compact, concise description, what might you do? And what we're thinking about as global guidance is even deciding what method should I use, PCA, and how should I look at it, and you know, what operators should I use? So think about the space of possible operators, and that you want to give some guidance to what should you do and in which order, because typically there's a fairly long analysis pipeline. So I'm calling that global guidance, and then another way to think about guidance is what should I do for a particular operator? Things like, what are the parameters? Have I set them right? So in the case of PCA, it would be, well, how many principal components should I even aim for? And what? So again, I'm not going to go into details about this system. I'm just going to grab one example. So what we did in DimStiller was say, let's try to identify workflows that people have systematically in doing this kind of data analysis, and think of them as a sequence of operations, and actually give the user guidance in stepping through them. And a key thing is that for each operator, have it set up so that they automatically get some level of local guidance. So let's take this example, which is if you're going to do dimensionality reduction, how do you pick the target dimensionality? And the answer in many cases is, well, I pick 2, because that's dimensions on a piece of paper. And they don't actually think deeply about what is the dimensionality of my data set. Whereas it has been well known for over 40 years that it's effective and useful to actually look at a scree plot of the residual error. But many, many, many middle ground users don't actually know this, don't have the idea that they should try to understand what is the true dimensionality of my data before running a reduction. So what DimStiller was designed to do is say, let's build this in to give the visual guidance to people as they're walking through the data analysis process. So back to methods and outcomes, one of the things we did here is try to talk a lot to users and understand what are the workflows they do in this kind of data analysis. And with the preliminary results from the DR in the Wild project, we did come up with several, and those are the ones that we built in as examples, and we also tried to make sure that the system new ones as people uncovered them. So in terms of outcomes, what we built is a prototype system where our buzzword was DR for the rest of us. That is, for people that aren't necessarily already experts in dimensionality reduction, in part because we found that a lot of people were using these methods with only partial understanding of whether or not they were appropriate. So for the then what on this, the question is, well, who owns guidance? And once you put on your guidance hat, you start realizing many, many people might benefit from some guidance. And it's not just middle ground end users of DR. So this question of guidance, what about some guidance on what sorts of visual encoding techniques are appropriate? So this is now coming down to the visual encoding technique level in the nested model. So this question of how should we show the results to people? One question is, if you're the developer of a system, how should you actually show that reduced data, and also understand if you're the developer of a metric, there have been some that were proposed that were stating as that they were capturing the characteristics of human perception that turned out to actually be not so well guided. So let's look at these examples. This was some work with Melanie Torrey and some of her later students, David Sprigg, Fuchu Wu, and Ming-Yen So. And it was about this question of looking at dimensionally reduced data. So there was this interesting phenomenon of people making information landscapes, where they would take DR data and they would say, we need to build landscapes. So, right, we're in the land of mountains. People are saying we need to build mountains out of our dimensionally reduced data. And so specifically that if you had a set of points in 2 dimensions, you would calculate some kind of density of the points and then encode that as height to make the terrain. And I'm calling this an oddly popular choice because there's a lot of work in human perception that implies that using 3D in a situation where you have abstract data and don't necessarily need to use 3D has a lot of known issues with occlusion and perspective distortion. And so the question is, why do people keep insisting that they should use landscapes? And there were a lot of assertions in papers that kind of talked about pattern recognition and, let's invoke the spatial reasoning, and, well, it's familiar, there's mountains just out the window, so shouldn't we really need mountains for our abstract data? So we thought, let us investigate in a little more detail. Let's try to understand what's an abstract task that maps to this kind of use of landscapes. So when thinking about what's the abstraction here, we came up with the task of, well, let's think about visual search, where what you're trying to do is think about spatial areas in some kind of estimation task. So specifically, let's think about estimating which cell in these 2 grids has the most points of a particular target color. And so that turns out that in domain-specific examples, that might be questions like, where in the display are people with high incomes, or does this area have high education levels, or correspond to a work sector? And so we picked this because the complexity is not completely trivial. It's not just a simple answer that you can answer in under a second. So it's fast enough response time to do a lot of user trials in a lab study, but it's not so trivial that it's just a perception task. And also, we did some pilot testing of what people are doing in real data analysis and decided that this abstract task was indeed a frequent subtask. So this question is really well suited for lab studies. You have a specific question that you can treat in a very abstract way, and you want to actually test human time and error. So we tested actually several configurations. Here's the 3 I'm going to focus on here. What if you just showed your points as points? Versus what if you showed them as this full-on 3D terrain? And then actually let's think about a sort of a thing to disambiguate the question of landscape from use of height coding. And so our hypothesis was stop it with the landscapes and just use points. And the result was yes, you should just use points. People are 2 to 4 times faster and an order of magnitude more accurate if you just actually show them the points. This is a specific case of dimensionally reduced data. And then if you do feel the uncontrollable need to use landscapes, 2D is better than 3D in this case. So it's an interesting case where redundantly coding with both color and height is worse than just coding with color alone. It doesn't give you an accuracy difference, but it does give you a significant speed to not use the height and just use 2D. So in terms of methods and outcomes, this was a very nice example of when lab studies are helpful. You've got a fairly clear hypothesis, human time and error are interesting, and then you can actually run a carefully controlled experiment. And so the outcome was that we could give fairly clear prescriptive guidance for what people should do in visually encoding, namely, stop doing 3D landscapes. Now, then you might think, aha, there's many other things, and let's attack all of them with user studies. And there's some interesting cases where a user study is not the right answer. And let me now tell you about one of those. So this was a fairly complex chain of events to get to this paper. It's a taxonomy of the factors in visual cluster separation. And this was joint work with Michael Sedelman, Tatu, and Tori. Now, there's a pretty simple idea of cluster separation, which is simply, are these clusters on top of each other or not on top of each other? And this is a judgment people can make fairly easily. And let's actually think about a whole spectrum from completely overlapping, partially overlapping, being right next to each other, separate, and then distant. So this sounds simple. a lot of people have proposed metrics to try to capture the idea of cluster separation with something that we can measure. And so there's even been quite a flurry of recent work, both from Sips and Hanrahan and from Tatsu and Keim, about saying we've got a matrix, we're trying to automatically detect which of the entries in that matrix are going to be useful to look at. Let's just have some algorithms that can say which ones of these are good. So we thought we were done, and we really wanted to use these to give guidance, and we wanted to build them into a system. And so one thing to keep in mind is that the goal of these metrics is not so much to use while iteratively refining a clustering, but to try to capture whether or not a human will notice that clusters are separate. So this really was trying to capture human perception rather than being used in the course of computation. And we thought we were okay in part because people had done these user studies already and had validated these measures. So we tried to use them, and we hit a bit of a brick wall because there would repeatedly be an automatic metric saying that something was good, but a human would say, but that's not good at all. No, this is not a nicely separated cluster. So the question was, what's going on? And so we started understanding a difference between what we'll call a user study and a data study. Now, a user study is what a lot of people are familiar with. There had already been some done for these cluster measures, and what you do is you run a small number of data sets past a large number of users. And we actually started going down this path ourselves because we thought, well, maybe they just didn't do the study right. Maybe, you know, they were sloppy. And it turned out that the answer was not that they had the techniques wrong, but that there was a key thing that was missing, which was a sufficiently broad variety of data sets. And it's kind of intrinsic to the design that if you're running lots and lots of users, you have hard limits on the number of data sets you can show them. So we decided to flip it and do this thing we're calling a data study, where you have a small number of users and look at a large number of data sets. So literally hundreds of data sets and just 2 users, and we wanted to compare the results against these automatic algorithms. So in the end, we ended up having 2 humans look in detail at 816 data sets, where there were what we're calling a data set instance is the combination of a data set, a dimensionality reduction method, and a visual encoding method. So we looked at 33 real-world ones, 44 carefully designed synthetic ones. Notice how this is pre-classified data. So there was some idea that there's a classification, which here we expressed as a color coding. And we're trying to guess whether, or we're trying to show whether this classification actually shows cluster separation. We used PCA, robust PCA, because they're commonly used, Glimmer MDS, the algorithm I told you about easier, and a nice algorithm out of the machine learning literature called TSNE that's specifically designed for separating out clusters visually. And then we looked at 2-dimensional scatterplots, 3D scatterplots where you could interactively rotate to try to resolve the occlusion questions, and then 2-dimensional scatterplot matrices. So just to give you a quick sense of what these measures were, they were called different things in the various papers, but our more evocative name is centroid measure. And that's saying, well, we're going to check, here's an example of a data set where we're seeing the centroids for the 3 classes. It gets a fairly high rating. A point is rated as good if it is closer to its own centroid than to those of the other clusters, and as bad if, in fact, it is closer to some other cluster's centroid than its own. So this is an example of something that was highly rated. Yes?
So the data was all spherical. So the axes were scaled so that the variances were same on all axes.
Yes. I believe that is true, but I would have to double check. But I'm fairly sure that it's true in the 2D projection, well, or the 3D projections. Yes. But I will double check after. But I'm fairly sure the answer is yes. An interesting thing in terms of methods is that we use an analysis methods that probably a lot of people in this room haven't used, which is a qualitative method out of social science. And it's called coding, but I don't actually mean hacking code. In this case, what coding means is that you gradually build up a set of codes to assign to something that you see. And so typically there's a 2-phase thing where you gradually build up a set of basically categories or labels or keys to the data that you're looking at. And then when you're fairly sure that you've got the full set and you've gone through and actually done the coding of all of your data, then you go through and you try to construct hierarchical relationships between these codes so that instead of, say, a few dozen or even more things that you could consider at the leaf nodes, you build up then some kind of hierarchical structure to put some multi-scale structure into this code set. And so we use this approach to try to evaluate, first of all, when do the metrics align with the human judgment, and if they don't align, then why? And so, for example, some of the factors we found, and some of these factors will not be a shock, right? Well, what affects things? Whether there's outliers, the actual shape of these clusters, whether or not there's a visual split for the things that are supposed to be in the same cluster, whether, for example, things are clumpy versus equidistant. So these are some of the measures. And what then we ended up doing was building a taxonomy from these factors into reasons, and then trying to figure out where are the areas where the metrics failed onto this taxonomy. So once again, I'm not going to go into detail about this. This was the full taxonomy we came up with, where all of these end up being contributing factors to, down here in the lower right, what actually affects the perception of class separation. What I'm going to do is just go through a few examples to give you a flavor of why this might be interesting. So at the high level, the interesting thing was the measures failed half the time. This was a surprisingly big number. And when you look at real data sets, it was even worse. They actually 68 or 65% of the time. So one of the things we did is we looked at the failure cases to try to understand what's going on. And what we found was that many, many more of the failures were false positives versus false negatives. So our conjecture is that the algorithm designers were worried more about the false negative case and kind of neglected the problem of positives. So let me give you an example of that. Here's a false positive example, again, with the centroid measure, where what we get is a fairly good number from the metrics. These actually go between 0 and 100, where 100 is best. And there's this false positive problem where the metric itself was actually coming up with numbers that were good, because it turns out that most of the points were closer to their centroids. What's really going on in here was that there were classes of different geometric sizes. There was a lot of overspreading. There were large geometric areas on the projection versus small ones, and so there was this kind of overspreading. In this case, the data set was a Gaussian synthetic one, and we were using MDS. But the part I want to focus on is, well, what mattered in the taxonomy. In this particular case, it was whether you had a variance of size. And clearly, a lot of the validation had been done with data sets of similar, where the classes had similar size, as opposed to really disparate sizes. So to cut a long story short, we did a lot of analysis, and it turns out that this metric really worked. Clusters were roughly round, and there wasn't more than one dense spot, sounding kind of Gaussian. There weren't really many outliers, and you had both similar geometric sizes and number of points in the classes. And when these assumptions weren't true, then the metric tended to fail. And of course, the punchline was that these were rarely true in the real-world data sets. For those of you who are familiar with the scagnostics work from Wilkinson et al., there's some interesting parallels here where we're coming at the same question from very different directions. And what Wilkinson was worried about with scagnostics was, do we have a nice, crisp way to mathematically describe and algorithmically instantiate some measures of scatterplot shape? And then what we were interested in saying, building up just from what humans are noticing, where do these two things actually intersect? So we aren't worried about whether we can algorithmically instantiate them, but we are worried about what do people notice. And so there are some interesting areas where they actually come together. We both had this idea that matters, things like outliers matter, things like the sparsity of the data set matter, but there's a lot of other places where there's quite a bit of detail in this taxonomy that you can't get out of the scagnostics work. Skinny and narrow. So back to methods and outcomes. In this one, it was this interesting method that we're actually hoping people use, a qualitative data study. Most of the qualitative work that's gone on in visualization has been very much exploratory work in terms of understanding how people are actually doing tasks, as opposed to looking at data sets. So we do encourage more folks to do this. We think it's an interesting method. In terms of outcomes, what we had was a taxonomy that we could use to understand some current problems, which were these previously proposed measures, and also to try to figure out what should we do more of in the future. And that's both for developing better measures and metrics, but also for some problems about techniques and systems. And there's more details about that in the paper. So coming back to my then what? So then there's this question of how do we go from just helping them to do DR better to understanding when should they even bother doing DR at all? When do they need it? And this question of when do people use DR? Well, the answer is sometimes they don't. You might think. And how to actually figure that out in advance rather than after you spent a couple years on a project and then you are very sad. So here was an interesting work. I don't often publish negative results, but this was one on reflections on QuestViz, which was joint work with Aaron Barsky and Matt Williams. And this was an interesting example where we had people come to us who were doing environmental sustainability modeling. And they had the simulation model that was a high-dimensional model with inputs and outputs. And we decided to help them understand what was the relationship between input choices and then the outputs of their model. And we would do a kind of classic visualization approach of having some linked views and showing them their output with dimensionality reduction. And after quite a long time, we discovered that really the answer was no, they did not need dimensionality reduction at all. And it was an interesting problem of a mismatch all the way up at the top level of that nested model at the domain problem characterization. And it turned out what they wanted was the general public to talk about issues and change their behavior. They did not, in fact, want the general public to do data analysis on the outputs of their models. In fact, for them, that was a sidetrack. And in retrospect, that was obvious, but of course, at the time, it was not at all obvious. And so actually, this failure case was one of the motivations for coming up with this nested model of understanding that all the visual encoding in the world couldn't solve a problem at low level. But that brings you to, so gosh, how do we just avoid falling into these pits all the time? How do you know what a user needs? And it turns out talking to them is necessary, but not at all sufficient. And we do now have some level of answers of trying to think about what's the right, not just set of methods, but actually methodology for doing this kind of problem-driven research, which is a lot in the Viz field is in the form of these design studies where you really are saying, here's the problem, I'm going to try to solve it. And DR is one of many possible techniques that you might need. So we actually have some recent work that was published at last year's InfoViz on the methodology of design studies, and that was joint with Michael Tamara and also Mariah. So this problem of how do you do a design study, it turns out that it's a fairly long and winding road, and there's many places to fall into the quicksand. And the reason we know this is that between the three of us, we've done about 21. And there's lots that were successes, and you probably know those ones better, and there were some that were failures, and in particular, there are a lot of lessons we learned along the way. And so what was in this paper is a whole set of definitions to help people think about it, a proposed 9-stage methodology for how it is that you can try to understand how to do this kind of work, and in particular, 32 different pitfalls and how to avoid them. So because we're running low on time, I'm going to talk about just one, but keep in mind there are 31 others. So a very common case of a pitfall premature publication, particularly that will bite people that are used to doing a lot of driven work that want to switch to doing more problem-driven work. And a very useful metaphor is the horse race when you're doing technique-driven work. And you've got to be first. And if you're not first, then your paper probably won't get in. So really, as soon as humanly possible, you should get that paper out the door. A very different metaphor, which is perhaps more appropriate for problem-driven work, is, am I ready to have this new musical piece? And typically, that's not a horse race. And it's not that anyone is doing exactly precisely what you're doing, but you want to figure out whether the thing you're doing is actually ripe and mature and ready. And in this, all of your reflexes of horse races actually do you wrong, because if you do your piece too soon and then later you actually do something better, well, how do you publish that without stepping on your own toes? Or, in retrospect, realize that you published work which was maybe not quite strong enough. So, in terms of methods on this paper, there was a mix of both introspection of our own lessons learned, not only as but also reviewers, because I've reviewed a remarkable number of poor design study papers. And we were trying to be systematic about what were these pitfalls. And also a lot of search, because what we hoped at the beginning was that HCI would have the answers. And if I just found the right paper, I could read it and I would know what to do. And there's some interesting analysis at the end of the paper about why none of the existing HCI methodologies were exactly the right thing, and what are the similarities and differences between some of them and the problems that we think we face as Viz people. And so the outcomes here were some prescriptive advice in terms of methodology. And here the analogy is that methods are like ingredients, and methodology is like a recipe. And so even having the full set of ingredients doesn't necessarily give you the recipe you need. So what we try to do is say, here's a way to do this kind of problem here in work. Not the only way, but a way. And specifically some pitfalls that you might want to try to avoid. And what I want to say just as a kind of meta point is that meta papers are very much worth doing. And anytime you can think about the methods and methodologies, it's useful to do and to try to write down for others. This is not just about design studies, but any kind of work. So in terms of steps going on, hopefully you'll see the final results from DR in the Wild. We think we learned some really interesting things that have really shaped our own thinking. Another example of a place where previous methods didn't quite work is dimensionality reduction in journalism. So there's a guy, Jonathan Strait, at the Associated Press, who saw that we'd released Glimmer and tried to run it on a WikiLeaks data set and discovered that it was falling short. And we've actually done some initial work about trying to come up with better methods to find the structure in this data. It's already been deployed to a bunch of journalist users through the Overview project because he got some funding from the Knight Foundation. And we really have found even more interesting real-world analysis needs that are not yet met. Stay tuned for that. So to wrap things up, what I've tried to do is give some examples of how going back and forth between different angles of attack can actually lead to some interesting questions about, well, what work should I do next? And what I found is that trying to scratch my own itch has often led me to these problems that have had relatively high impact, because what happens is, as I do evaluation, then I figure out what I actually want to build next in terms of techniques. And then when I'm wrestling with how to build things, I end up understanding, well, here's the study I really would run. Okay, I'll be that people. And to actually make, I think the taxonomies are very abstract, but I find that systematically they help me decide what to do next in terms of major open problems. So I feel like often your goal is to find these mismatches, which is where you could do better. Is there a mismatch between the principle and the practice, or between the practice and the needs of the users? And the way to find these is to truly have this parallax view of all three: principles, practices, user needs. So to wrap up, this talk itself is already posted, and all the papers I referred to are up on that page. I'd like to thank NSERC for funding most of this work, all the folks I've worked with on this, in particular folks in my group and others for feedback, and mention that the person behind a number of these projects, Stephen Ingram, is going to finish his PhD, and after he finishes a postdoc in my lab, will be interested in hacker analyst jobs. He doesn't want to go into academia, but he does want to do some interesting hacker analysis stuff either in industry or lab. So that is my advertisement for a hiring opportunity. And now I'm happy to take questions. So thanks.